Problem number 2, find the most economical proportions of a cylindrical cup. So what we see here that Maxima and Minima has applications in engineering, because in engineering, especially in materials engineering or any type of engineering, you want to create the most economical proportions as always. No? Engineers are assigned to do that problem. It's actually called optimization. So here it is just a simple problem because it is a simple shape, a cylindrical cup, but in real world situation that would be a more complex shape for that matter. So simple cylindrical cup. Okay, we draw here a cylindrical cup, and we want to find out the most economical proportion. Of course, the fixed thing here is the volume of the cylindrical cup. Okay, you can create a tall cylindrical cup, a small cylindrical cup, but it would have the same volume. It would contain the same amount of liquid in it or fluid in it. But the question is, what is the shape, or what is the proportion? What are the dimensions so that the least amount of materials would be used? So for the least amount of materials, that would be dictated by the surface area. Surface area of our cylindrical cup. And the surface area of the cylindrical cup that we are seeing here it's composed of a body. Okay, so the body is a rectangular surface. Okay, and the bottom part of our cylindrical cup, and that is a circle. Okay, so what is the area of a rectangle? It is length times width. Okay, but the length of the rectangle here, is actually the circumference of the circle. And the circumference, we know the formula for the circumference is 2 pi r or pi d. Depends on what you prefer to use. And then next is the area of the circle. So it is simply pi r squared, as we know the formula for the circle. So the width here, is actually the height of the cylindrical cup. So that is the height of the cylindrical cup. So the surface area, so let's just say that's S. The surface area is equal to length times width for the rectangle, and that would be 2 pi r, the length, times h, and then pi r squared. So what we see here is we have two variables. Okay, RH, the radius, the height. Okay, so we need to have another equation, and that's where volume would come in, because as I've told you, volume is fixed in this situation. So the volume of a cylindrical cup is actually equal to the area of the base times the height. So the area of the base here is pi r squared times the height. So if we will solve for h, say for example h, because r has a square, so it's simpler to solve for h, then h would be equal to v over pi r squared. So let's go ahead and substitute that to our, let's say this is our equation 1 and this is our equation 2. Let's say we substitute to our equation 1, which is the surface area. So S will be equal to 2 pi r times h, so v over pi r squared. Then we add the area, pi r squared. Okay, so we see that we can cancel some terms here. Pi can cancel, okay, and also r. Okay, so S is now equal to 2v over r plus pi r squared. Okay, so let's write it down here again. S is equal to 2v over r plus pi r squared. Okay, so this is now, we can now get the derivative of S with respect to r. V being a parameter or a constant parameter here. Okay, remember that. So this will be negative 2v, then derivative of r is 1 over r squared. So we we implemented the formula, the derivative of c over v. Okay, and then pi r squared. So pi is constant, so pi times 2r. And then let's equate our first derivative to 0. So 0 is equal to 2v over r squared, negative 2b over r squared, plus 2 pi r. And then 2v over r squared is equal to 2 pi r. We can see that we can cancel out 2. And then, let's continue here. We now have v over r squared is equal to pi r. Or we have v is equal to pi r cubed. Okay? But v, the volume, as I've told you, is equal to the area of the base, pi r squared, times the height. So it's equal to pi r cubed. So pi cancels out. Pi cancels out. R squared will also cancel out. And we are left with this proportion, or this answer. The height is equal to the radius. Okay? So what does that mean again? So our problem is to find the most economical proportion of the cup. So therefore, the most economical proportion of a cup is where your height, the height of the cylindrical cup, should be equal to the radius in order to create the most economical proportion, or again, in order to use the minimum amount of material. So last example for maxima and minima. So let's have some example in analytic geometry. Application of maxima and minima in analytic geometry. We have find the shortest distance of 0.50 to the curve 2y squared is equal to x cubed. So I got a grapher and graph that curve, this one, 2y squared is equal to x cubed, and this is the graph, or this is the curve that was produced in that grapher. Okay, and let's locate 50. So this is 4 and 6, so 5 would be somewhere here. 50, and we want to find the shortest distance. Okay, so let's say that so we want to find this distance, the shortest distance. So I'm not saying that that is the shortest distance at the moment, but just to illustrate, if I draw a line, I want to get the distance that would be the shortest from this point to the graph in at hand, which is 2y squared is equal to x cubed. So we want to get that. So we also have a corresponding point here on the graph, which is xy, an unknown point, from which we could solve for the distance. Okay, if we were to apply the distance formula, so it will be equal to the square root of, so that would be x minus 5 squared plus y minus 0 squared. Okay, that's it, the distance between those 2 points, and that point is still unknown. Okay, so the distance is equal to the square root of x squared minus 10x plus 25 plus y squared. Okay, so we cannot get the first derivative yet because we have 3 variables and we want to simplify. So we will get an equation here. We have 2y squared is equal to x cubed, and therefore y squared is equal to x cubed over 3. So let's go ahead and substitute that to our y squared. So d is equal to x squared minus 10x plus 25 plus x cubed all over 2. Okay, so let's go to our next page. D is equal to the square root of x squared minus 10x plus 25 plus x cubed all over 2. Okay, let me just check if I wrote the same equation. So now we can derive. We can get the derivative of the distance with respect to x. So let's just call it d prime. So we have 1/2 times x squared minus 10x plus 25 plus x cubed over 2 raised to negative 1/2, and then derivative of this one. So this will be 2x minus 10 plus 3x squared over 2. Okay, so we will equate this to 0. This will be equal to 0. So we have 1 over, I will write this first, 2x minus 10 plus 3x squared over 2 all over 2 times the square root of x squared minus 10x plus 25 plus x cubed all over 2. So we can go ahead and multiply the denominator, this one, to 0, so that the simpler term, the numerator will just be left with us. So we have 0 is equal to 2x minus 10 plus 3x squared over 2. Let's go ahead and multiply 2 to simplify the quadratic equation. So we have 0 is equal to 3x squared plus 4x minus 20. Okay? 0 is equal to 3x squared plus 4x minus 20. So if we will just factor it, 3x, x, so this would simply be 10 here and 2 here. So we have negative 20, okay, and positive 4. So we'll just go ahead and write positive here and negative here. Okay, so check. 10x minus 6x is 4x, and then 10 times negative 2 is 20, and 3x times x is 3x squared. So for the values of x, we have x is equal to negative 10 over 3 and x is equal to 2. Now, what is true? Okay, between these two values of x, what is true? Let's go ahead to our graph. So this is the image of our graph. Okay, we can see that it is on the positive side of the x-axis. So this is x-axis, that is y-axis. So there is no value of x that is negative. So therefore, this value will simply be nullified. Okay, and we will choose x is equal to 2. Okay, so when x is equal to 2, our curve's equation is equal to 2y squared is equal to x cubed. And when x is equal to 2, so 2y squared is equal to 2 cubed, that would be 8, and y squared is equal to 4. So therefore y is equal to plus and minus 2. Okay, which is true because we have here a symmetrical curve, and when x is equal to 2, we will hit here two values, okay, as we can see in the curve, 2 and negative 2. So actually, the shortest distance, okay, the shortest distance would be this one. Okay, instead of my first drawing, that would be the correct position of the shortest distance of the line. But I don't know it yet in the first part. So now that I have solved it, I see that that is the shortest distance. So either this one or the line here where y is equal to negative 2. But they would produce the same length. Okay, so let's go ahead and solve for the distance from 2 to, let's say, from 2 to 5, 0. So the distance is equal to the square root of 5 minus 2 squared plus 2 squared. So this is 3 squared, so that would be 9, and 2 squared would be 4, so the distance is equal to square root of 13. Okay, so that is our answer for the shortest distance from 0.50 to the curve 2y squared is equal to x cubed.